Good afternoon, everyone. Here I am welcoming all for this another webinar session, knowledge sharing webinar session. And first of all, I wish you a very happy new year to all. Hope everyone is doing well. And surely this webinar on transformer testing and transformer winding resistance measurement and the related scope product, that is our TRM series. This will helpful and useful to everyone. During the presentation, firstly, I will give a presentation, and during the presentation, if you are having any queries, then put into the chat session. And after the presentation, we will try to cover all the questions. So today's topic is transformer testing and transformer winding resistance test, and specific point, that is how to select a transformer winding resistance meter, that is transformer ideal transformer winding resistance specifications, and our product series TRM series, that is transformer resistance measurement series. So overview of the today's webinar is we will see the types of the transformer based on the applications, parts of the power transformers, transformer faults, then causes of the failure and test on the power transformers, then testing classifications and which major test that we need to conduct on the power transformers, then applicable IEC, that is IEC, Indian standard and IEEE standards, then importance of the winding resistance test, then brief about the working principle and test concept of the winding resistance measurement, then measurement types. Then we will see our scope introduced TRM series. There are various models are there. Then our product models, TRM specifications and advanced features. Then how to select a DC test current. Then connections from the instrument to the device under test, that is to the transformers. Then demagnetization basics, what is demagnetization and how to do a demagnetization, like that. Then OLTC types, that is on-load tap changer types, and testing of the OLTC to check the healthiness of the OLTC. Then resistance versus time graph, that is required during the hit run test. Then user interface of the instrument, how to operate the instrument, and ideal transformer winding resistance measurement meter specifications. So this is overall overview of the today's webinar. As everyone aware about the power system, that is power system having a 4 stages, that is generation, transmission, distribution, and last one is the consumption, or we can say it is a consumer level. So generation, actually the generation, it is normally voltage generated at the generator side, it is 3.3 kV or 6.6 kV or 11 kV. After that voltage, that is 11 kV, is converted, that is stepping up to the 33 kV or 66 kV with the help of transformer, that is step up transformer. Normally it is, we are saying at generator transformer. And after the 33 kV and 66 kV, it is converted into above voltage levels, that is 110 or 220 or 400 kV. That is, we are saying it as a power transformer, that is used in the transmission level. And after that voltage, that we need to convert to the lower voltage level, that is up to 11 kV or 440 volt. That is, we are saying at a distribution side transformers, that is step down transformers. And last one is the consumption, that is the at the home level, that is single phase supply, that is 230 volt. If it is a 3-phase supply, then 415 volt. So it is divided into 3 parts: generator transformers, then transmission level transformer, that is power transformers, and distribution side transformer, that is distribution transformers. So here some types of the transformer based on the applications. The first one is the power transformer, that is to stepping up the voltage. Then distribution transformer, to step down the voltage, that is used in the distribution side. Auto transformers, that is to for the interconnecting two systems to converting into the same voltage level. Then reactors that is to reactive power compensation purpose. And last one is the instrument transformers. Instrument transformers having three types, that is current transformer, voltage transformers, and capacity voltage transformers. That is used for the metering, protection, and somewhere it is a special protection type. As everyone aware about the parts of the power transformers, so here you can see this is a transformer, and all the types, that is core, that is 3-limb core type core is there. Also somewhere 5-limb shell type core is there. Then LV winding, then HV winding, then we can say tapped winding for the voltage regulation purpose. Then LV bushings, HV bushings, then all load tap changer, then motor drives to operate the OLTC, then tank, conservator, and radiators. So these are the all parts of the power transformers. And here you can see, so these 6 are the main parts of the power transformers, and we will see and we will majorly look on these parts only. That is, first one is the core. That is core used in the transformer, that is silicon steel. Winding, majorly it is a copper winding. Bushings, there are 2 types of the bushings, that is OIP and RIP, that is oil impregnated paper and resin impregnated paper bushings are there. OLTC, on load tap changer. This is very important component in the transformer, that is used to regulating the voltage without interrupting the load current. And about 30% of failures occurs in the transformers due to the OLTC problems. Next one is the tank and oil. So basically oil used in the transformer, there are 3 types, that is mineral oil, then silicon oil, and ester oil. So basically are about 90% in transformers we are using mineral oil. And in mineral oil there are 2 types, naphtha based and paraffin based. Out of that, naphtha based is normally preferred in the transformer for the cooling and insulation purpose in the transformer. So here you can see transformer faults. With the IEEE paper, I have taken this data. So about 29% faults occurs due to the electrical disturbances, that is due to internal or external electrical disturbances. Then insulation deterioration, the problems occurs in the transformers or fault occurs in the transformer, it is around 18%. Then inadequate maintenance, that is improper maintenance, irregular of maintenance, the fault occurs in the transformer, it is 13%. Then loose connection or poor connections, open connection, the fault occurs in the transformer, it is 13%. The moisture content in oil or insulation, the fault occurs in the transformer, that is 7%. And due to the lightning or due to the insulation failure, due to the lightning, the fault occurs in a transformer. Because of damage of the insulation, it is 16%. And other that is 4%. So this is all about data I have taken from IEEE paper. Similarly, one of IEEE paper I have taken this data also. So here you can see, so these are the major parts, and about 26% of problems occurs in the transformers, that is due to the damage of the OLTC or problems occurs in the OLTC. Then due to winding failure or winding damage, the problems fault occurs in a transformer, that is 34%. And failure or problems occurs in a tank due to the damage in a tank, that is around 21%. The failure or problems occurs in a bushing due to the insulation deterioration, it is 20%. And due to the fault occurs in a core, that is 5%. And other, that is cooling or secondary part, the fault occurs in a transformer, it is 20%. So here you can see around 60% of fault occurs due to the problems or fault or damage of the winding, and fault occurs in a OLTC. So we need to take care majorly on a transformer winding and transformer OLTC healthiness. So next part is the transformer testing. So here I am summarized some brief about the transformer testing. So here you can see the left part indicate this is a winding, and the reason behind the winding failure, the main failure or cause behind the winding, that is interturn short, then open winding or poor connections, magnetic imbalance, then increasing copper loss, then mechanical damages in the winding due to the in the transportation or shipment of the transformer, insulation degradation, then rise in a winding temperature, then partial discharge or hotspot. So these are the main reasons behind the failure of the winding. And with the help of different preventive and diagnostic tests that we need to carry out to check the exact reason behind the failure of the winding. So here are the total tests that we need to carry out to find out the interturn short that we need to do with the help of turns ratio test, winding resistance test, excitation current test, short circuit test, SFRA. Similarly, for open winding and poor connections, so we can check with the help of turns ratio test, winding resistance test. Similarly, other remaining tests that we need to carry out to check the exact reason behind the failure. Here you can see SFRA test to check the mechanical damages in the winding, then capacitance and tan delta, then partial discharge to check the insulation degradation or moisture content in the insulation. Similarly, a partial discharge test is to check the partial discharge or hotspot occurs in the winding. Similarly, in the core, some reasons behind the failure is core overheating, then iron losses, increasing the iron losses, that is no load losses, mechanical damages of the core, and harmonics on the low load current. So with the help of different tests, that is excitation current test, open circuit test, that we need to find out exact reason behind the failure of the core. Similarly, bushing. So there are different types of the test, that is capacitance, tan delta, insulation resistance, lightning impulse, switching impulse, power frequency voltage, like that. Then insulating oil to check the oil quality, moisture in the oil, dielectric strength, rise in oil temperature. So we need to conduct oil breakdown voltage test, dew point, then flash point, fire point, tan delta, pour point, viscosity test, like that. Similarly, tank, we need to check visual inspection will be there, and earthing resistance testing is there. Similarly, for OLTC testing, for on-load tap changer healthiness testing, we need to do operation of the OLTC, then to check the continuity of the OLTC, then there is a winding resistance of each type is there. Resistance of each type, we can analyze the condition of the OLTC, and also there is a one important test that we need to carry out, that is dynamic resistance measurement. We will see what is dynamic resistance test and how to do with our instrument in the upcoming slides. So these are the applicable IEC standards for doing a testing, doing a design during the manufacturing. So all the tests have given the testing related data. That is for the power transformer, the applicable IEC standard is 600. Distributed transformer is also same IEC standard, that is 60076. For power transformer, the IS standard, it is IS 2026. For distribution transformer, it is IS 1180. Similarly, other IEC, applicable IEC and IEEE standards are there for your reference purpose. So here you can see I have captured some major tests that we need to carry out on a power transformer. Here you can see the name of the test, that is winding resistance, turns ratio, vector group, polarity, magnetizing current, open circuit, short circuit, insulation resistance, demagnetization, dielectric test, OLTC. Remaining text like oil BDV, then magnetic balance, tan delta, SFRA, and temperature rise. So out of that, as I said earlier, around 60% of failures in the transformer due to the problems or fault occurs or damage in the winding, and problems occurs in the OLTC. So with the help of our TRM instrument, the all out of that 3 tests we can do, that is winding resistance, OLTC, and the demagnetization. So with the help of our single instrument, that is TRM instrument, we can do these 3 tests with, here you can see, so these are the applicable IS and IEC standards I have mentioned here with clause number. So for winding resistance, the clause number for the IEC 60076-1, clause 10.2. Here testing classification, as everyone aware about the testing classification. So there are different tests are there. That is, first one is the tap test, then factory test, then commissioning test, routine test, special test. The tap test is we need to do on first a prototype of a product to prove the ratings and specifications and characteristics. That is, this test is valid till there is a no design change. Factory test, that we need to carry it out to check the manufactured product is as per the rating. Similarly, commissioning test we need to do at the time of the commissioning. A routine test, that we need to check the healthiness or healthiness and condition check of the transformer, that will be conduct in once in a year or 6 monthly as per recommended by IEC or IEEE standard, or as per manufacturer or customers recommendations. Then special test, that is carried out as per the special requirement of the customers. So now we will, here onwards, we will focus on a transformer winding resistance test. And basically transformer winding resistance measurement on a power transformer, it is test is covered in various international standards, that is IEEE C57 2006, then IEEE 62 C62 1995, and IEC 60076-1. And similarly, this test is also covered in IS standards, that is IS 2026. So then next question, that is why we need to do a transformer winding resistance, or why we need to do a winding resistance test. So basically this test is very useful to identify the excess continuity in the power transformer in the winding circuit. Also to calculate the copper losses, to find out the copper losses are increasing or not. Then to find out the is there any interturn short or open turn happens or not. Then to find the defective tap changers or poor contacts integrity in the tap changers. Then find out the corrosion of the winding material. So basically DC winding resistance test identifies problems such as loose and poor lead connections, broken winding strands, etc. So these are the basic reasons, these are the importance of the winding resistance test. Then when we need to do a winding resistance test, basically this test is we need to conduct, or we need to do at the factory testing, that is to measure the winding resistance test. Then during the commissioning or during the installation, to compare the results with the factory test results, that is correct or not. Then during the commissioning, we need to ensure is there is no any deterioration during the shipment of the transformer from one location to another location. Then routine test, we can say to compare the results with that the factory test results, to get the assurance there is no any mismatch or no any server mismatch or opens or short circuit occurs. Then ensures the no deterioration due to the electrical stress or faults, to check the healthiness of the OLTC contacts and problems in the OLTC pin. So these are the winding resistance test that we need to do in the factory testing, during the commissioning, and during the routine testing. Then working principle. The working principle is that to apply DC current in the winding, that is we need to apply a DC current, and across the winding that we need to measure the winding resistance, that we need to calculate, we need to measure the voltage drop across it, and with the help of formula, that is V is equal to IR, that is I is equal to I by V, we can calculate the resistance of the transformer winding. So basically, Kelvin's four-wire methods are using to reduce the lead resistance. That is two wires for the current injection purpose and two wires for the measurement of voltage drop. The concept is, as I said, Ohm's law. That is, we need to inject a current, and across the winding we need to measure the voltage drop. That is, DC current is to be injected in the winding, and after the stabilization of current, that is constant current, or we can say stabilization of current, the corresponding voltage drop across the winding we need to measure, and with the help of formula we can calculate the resistance. So for winding and oil temperature measurement, we have to use some probes to measure the winding or oil temperature. Then resistance is calculated or equated to 75 degree. Actually, IEEE and ISC has recommended whatever resistance we have measured at any temperature, that is ambient temperature, that would be converted into 75 degrees Celsius to compare the results after testing during the commissioning or during the routine test. That will be helpful. So about winding resistance measurement, it is not just Ohm's law, that is R is equal to V by I. There is a lot more to it. That is, firstly is that winding is having an inductance. That inductance that we need to nullify. That is, we need to make a transformer core in a saturated. Saturation of the transformer is very important. Firstly, the transient state occurs, and after that we need to convert, or we need to reach at the steady state, and after that only, that stabilization of DC current is occurs after the saturation of core and after the reaching of the steady state. That after reaching steady state and after reaching stabilization of current, stable current, that point we need to measure the voltage drop. So this is not only Ohm's law. This is point that we need to nullify the inductance. That is, we need to we need to convert the DC current into stable mode. And after the winding resistance test, it is also important to return winding to the original state. That is, we need to do a demagnetization test. So we will see what is demagnetization, how it will be carried out on a transformer in upcoming slides. So measurement types. So basically, there are two types of the winding resistance measurement. That is, first one is the static winding resistance measurement, and second one is the dynamic winding resistance measurement. So static winding resistance measurement, it is to measurement of transformer winding of each step we can measure, and dynamic winding resistance, it is to check the healthiness and operation of the on-load tap changer. That is to check the behavior of the on-load tap changer. Now we will see the scope winding resistance meter, that is TRM series. So here you can see the TRM series. The scope introduces TRM series with different models having maximum current range, that is 10 ampere, up to 10 ampere, up to 25 ampere, and up to 50 ampere. So we are having three variants, that is up to 10 ampere, up to 25 ampere, and up to 50 ampere current range for winding resistance measurement. Also, we have optional facility for OLTC healthiness checking, then specially designed for the measurement of resistance, that is up to 765 kV in HV and EHV transformers. It is also used to measure the resistance of stator and rotor windings, generators, bus bars, reactors, isolators, and switching contacts, terminals, and connectors. That is, these are the applications of our TRM series. So here you can see these are our total models of TRM series. The first one is the TRM 103 and 104. These two models are for the 10 ampere current injection purpose. Here you can see. Then TRM 25 and 25 plus, these two for these TRM25, TRM25 plus, 50, 50 plus. These four models are advanced models that are so TRM25 and TRM25 plus stands, that is the current range having up to 25 ampere DC, and TRM50 and TRM50 stands, that is current range of that equipment up to 50 ampere. Here you can see some comparisons of our TRM series. That is, we have given some current ranges for various models. That is for TRM 103 and 104. That is from 10 milliampere to 10 ampere, and middle ranges are also there. For advanced models, that is TRM 25, TRM 50, TRM 25 plus, TRM 50 plus. Plus stands for TRM 25 plus and TRM 50 plus stands for these two models having a 6 resistance measurement channels, and TRM 25 and TRM 50 stands for these two models having a 3 resistance measurement channels, and TRM 25 and TRM 25 plus having current range up to 25 ampere from 10 milliampere is the minimum current range, and middle ranges are also there, that is 10 ampere, 5 ampere, 1 ampere and 0.1 ampere. For a larger transformer, that is about 250 MVA transformers having a substation current rating is around 2000 ampere or 1600 ampere, that we need to inject a high amount of current, that is up to 40 ampere or 50 ampere. For that we have designed the two models, that is TRM 50 and TRM 50 plus. That instrument is capable to do or capable to inject a resistance current up to 50 ampere. So here you can see 50 ampere, 40 ampere, 25 ampere, 10 ampere, 5 ampere, 1 ampere, 0.1 ampere and 10 milliampere. These are the current ranges. Then open circuit voltages we have provided for the lower models. It is 30 volt DC and 50 volt DC for the advanced model. This open circuit voltage is important for the fast stabilization of the current. Then resistance ranges we have provided, that is the instrument, all the instrument that is capable to measure the winding resistance up to 2000 ohm with best resolution 0.1 micro ohm. So as I said earlier, resistance channel, that is we have provided for our common instrument, it is 2 resistance channel we have provided, and for the advanced models for TRM 25 and 50 we have provided 3 resistance channel, and for TRM 25 plus and TRM 50 plus we have provided 6 resistance measurement channel. Also for the temperature correction facility we have provided automatic temperature correction facility is there. Then current versus time graph, that is to check the healthiness of the OLTC, we have provided 3 channels for the same. Then additional features that we have provided, that is printer, memory, internal memory. Then instrument we can operate with the help of software through PC. Then demagnetization is feature we have added. Then resistance versus time graph feature is also we have added. We will see the importance of resistance versus time, then demagnetization in the upcoming slides. Then display. In advanced models, we have given a touchscreen 5.7 inch TFT color touchscreen display for the easy operation to the users. Here you can see this is our advanced model, that is TRM 25, 25 plus, 50, 50 plus. This is molded case. Here you can see. So this instrument is useful for the easy transportation and easy operation. So as per the technical specifications point of view, so resistor channel, as I said, 3 for TRM 25 and TRM 50, and 6 resistance channels we have provided. That is, we can measure the resistance of both HV and LV windings simultaneously in a single click, we can say, for TRM 25 plus and TRM 50 plus. And we have provided 3 resistance channel in a TRM 25 and TRM 50 to measure the resistance of HV or LV in a single click. Best resolution for the measurement of resistance, that is 0.1 micro ohm. Then temperature channel we have provided for the temperature correction, and to convert it into 75 degree, that we have provided one temperature channel. Then current ranges, as I said, up to 50 ampere and up to 25 ampere as per the model. Then resistance, that is these four models can measure the resistance up to 2000 ohm with best resolution 0.1 micro ohm. Then open circuit voltage, we have provided 50 volt DC, that is to quick stabilization of the current. Then demagnetization facility we have provided. Then protections, that is back EMF, over temperature, accidental lead disconnection, auto discharge facility. So these protection facilities we have provided in the instrument. Then inbuilt memory, that is the instrument is capable to store up to 5000 or up to 10,000 results. Then features point of view, we have provided a TFT 5.7 inch color touchscreen display. Then fast stability of readings. Then instrument having a facility to measure resistance versus time graph. Then we have provided both Ethernet and USB facility. Then inbuilt thermal printer to take a print after the taking the readings. Then temperature measurement, automatic temperature correction facility to convert the temperature resistance measure at 75 degree Celsius. Then instrument features. So with the help of our TRM25 plus and TRM50 plus, we can measure 6 winding resistance measurement are provided for this resistance measurement. That is one-time connections to all windings of primary, that is all windings of HV and all windings of LV we can measure in a single click. So this will be helpful for reducing the time for the measurement. And another model, that is TRM25 and TRM50, that will be useful. That is, we need to connect instrument to either primary or either secondary to measure the winding resistance of the transformer. So instrument is not any need to compensate lead resistance, because we have used the Kelvin's 4-wire measurement method. Then we have provided different configurations in our instrument, that is current range selection facility we have provided. Then enable disable current measurement channels that we have provided. That is, user can select if there are 3 windings are there, that is R, Y, B. Then user can decide which winding resistance we can measure. So this channel only user need to enable, and other remaining channels user can disable them. Then temperature correction settings. Then winding material selection facility we have provided, that is for copper and aluminum. Then different tests we have added, that is winding resistance test, then all type winding resistance measurement facility, then OLTC continuity check, then demagnetization facility, then internal self checks and test connection check. So instrument is able to internal tester connections can check. Then optional OLTC healthiness testing facility we have provided. Also TRM series is basically having a facility to operate through software by PC or laptop. So this facility we have provided. Then this instrument is innovative and portable design for measurement of the resistance with a great accuracy and precision. Then instrument having a OLTC, that is automatic OLTC operation facility. Then we have provided touch screen display and simple menus to operate the instrument. Then facility to configure transformer ID and transformer all details, that is transformer rating, then location of the substation, transformer details, like that. Then instrument is having different current ranges provided with highly accurate and repeatable readings. Then date and time stamping facility we have provided. Thermal printer we have provided. Ethernet and USB facility we have provided. And instrument is lightweight and portable instrument, that is household in a rugged model, molded case. So these are the features of our instrument. So safety features that are important during the measurement or testing. that is over temperature facility, then over current, over voltage, accidental lead disconnection, then automatic discharge facility after the testing, and back EMF protection. So safety features that we have added in our instrument. Then about instrument. So instrument has gone through all the type test, that is IEC, IS, and recommended standards for safety compliance, then EMC compliance, that is electromagnetic compliance, then emission test, humidity test, environmental standards, safety standards, then storage test, then vibration test as per the IEC 60068 is there. For EMC, IEC 61000 is there, and for safety, there is IEC 611010. So instrument has gone all the type tests. So OLTC test. So instrument is able to check the healthiness of the OLTC. So to check the healthiness of the OLTC, so firstly, instrument is able to detect the discontinuity occurs during the tap change, that is during the tap changing, that is from one position to another position. The instrument can detect is there any discontinuity occurs or not. Then we have added another very important and required feature to check the healthiness of the OLTC, that is to check the diverter switch process, that is speed of the diverter switch and diverter switch operation with the help of current versus time graph. So we can measure the single and three phases simultaneously, that is RYB phases we can also measure in a single click or simultaneously. Then automatic tap changer facility. So instrument having a facility to automatic change the tap through instrument. So next question arises, that is how to select a test current. Basically, I have got some questions from some manufacturers and some utilities that how to select a current range, how to select an instrument. If there is a transformer of 200 MVA or 250 MVA, how much amount of current that I need to inject, that is how much amount of DC current we need to inject for doing a transformer winding resistance measurement. So as per IEEE 62 and ISC has recommended that for doing a winding resistance test, the typical current range is 0.1 to 10% of rated current. But it is also recommended never exceed rated current, that is never exceed 10% of rated current. Let us consider if transformer is having a current 10,000 ampere, rated current is 10,000 ampere. If it is a 250 MVA transformer is there, let us consider the transformer having a rated current 1000 ampere. So it is recommended that so about 10,000 means 10% of rated current we need to below 10% we need to inject. If test current is too low, that is below 0.1% of rated current, then whatever measured resistance is not a consistent, that is pending magnetic status will be there, and if less current we will inject below 0.1% of rated current, that will give a problems, that is to determine whether the current has reached a steady state or not. So basically, as per our recommendation is to inject up to 3% of rated current, that is from 1% of 1 to 3% of rated current. If transformer is having a rated 1000 ampere, then we are recommending to do a winding resistance test from 10 to 30 ampere. So this is a recommended range from our side. This is our now we will see the front view of the instrument and how to operate the instrument with various transformers, that is star delta, delta star, like that. So here you can see this is our advanced model, that is 6-channel transformer winding resistance measurement kit, that is TRM25, or we can say TRM50 plus and TRM25 plus. So here you can see we have provided one Here mains inlet. Then this is on off button. Then inbuilt printer we have provided. Then a touchscreen TFT display we have provided. Then total 6 measurement channels are there. That is, if transformer is star, then we need to connect RYB neutral directly to the transformer RYB neutral of primary, and similarly transformer RYB neutral of secondary we can connect. So in a single click we can measure resistance of 6 windings in a single click. Also here this is a earthing, master earthing point, that we need to connect transformer master earthing. Then as I said, the instrument is able to operate the OLTC in an automatic way. That is the OLTC cable that we need to connect here, and this another point we need to connect to the transformer control box, OLTC control box. Then temperature sensor cable that we need to connect here. Then DUT discharge indication that we have provided here. After the discharge, this LED will blow. Then USB and Ethernet facility that we have provided. So we can connect here pen drive or laptop through USB, and for the operation of the testing, we can do a testing through laptop through software. So with the help of Ethernet port, we can do the same. So this is about the TRM series front panel. Now we will see so these are the test leads that we need to use during the testing. That is channel cable. These are the channel cables. Then temperature cables for measurement of temperature. Then OLTC control cable, that is to change the tap automatic from the instrument. Then Ethernet cable to operate the instrument from laptop. Then this is a master earthing cable, and this is a mains cable. So these are the test lead set. Now we will see how to connect a instrument to the star-star transformer. Here you can see the instrument RYB neutral of primary that we need to connect directly to the transformer RYB neutral. Similarly, secondary RYB we can connect to the transformer RYB neutral. So in a single click or one-time connection, we can measure resistance of 6 windings. Similarly, for star delta, we need to connect all the connections, that is RYB neutral to the primary and RYB to the secondary of the delta. Likewise, if auto transformer is there, we can also measure the resistance of HV to IV, IV to neutral, and HV to neutral. So in TRM, we have added various tests. That is winding resistance test is there, that is WRT. Then all type winding resistance test, that is all type ATWRT, demagnetization, and OLTC test. Now we will see one by one. So WRT test that we have added to measure the winding resistance of a single tap. So with that mode, we can check winding resistance of a single tap. This is a standalone. This test we can do with the instrument and through the laptop. So simultaneous measurement of all phases is possible of one single tap, that is RYB phases of single tap winding resistance we can do. And current ranges, that is up to 50 ampere as per the model, up to 50 ampere if there is a TRM 50 or a TRM 50 plus. If it is TRM 25 and TRM 25 plus, so we can inject up to 25 ampere. And minimum current range that we have provided, that is 10 milliampere. If you select ATWRT, that is all tap winding resistance test, that is the purpose to measure the winding resistance of all the taps. That is in a single click, that is in a one-time connection, we can measure winding resistance of all phases of all taps. That is very time consuming test that we have added. That is customer or user need to only connect all the test leads from instrument to the transformer, and OLTC control cable from the instrument to the transformer OLTC control box, and the instrument is able to do all the winding resistance of all the taps in a single click. Then demagnetization feature we have added. Before giving some demagnetization point, we need to understand the purpose of the demagnetization, why we need to do a demagnetization. So basically the purpose of doing a demagnetization of the transformer is to nullify the residual magnetism after winding resistance test. Whatever residual magnetism, residual flux occurs in a winding, that we need to nullify with the help of demagnetization. So residual magnetism leads the high inrush currents that will put a great and unnecessary load on the transformer that will damage the transformer. So because of that, we need to do demagnetization test. Then what are the reasons behind the formation of the residual magnetism? So basically DC testing, that is DC current testing. The main reason behind the formation of the residual magnetism is the transformer winding resistance test, that is DC current test. So because of that, some residual magnetism will be there, that is we are injecting up to 10% of rated current in the winding. That will what happen, this level of DC current makes the transformer core magnetized, and once the test is completed, the transformer is discharged, but transformer is not demagnetized because some residual flux will be there, and that we need to nullify. And second reason behind the formation of the residual magnetism is the transformer shutdown. If we do a shutdown, if we need to do a shutdown, we will give command to the circuit breaker through relay to break the circuit. So at the time of circuit breaker breaking operation, the current will not be at a zero crossing point. So some residual or remaining flux will be present, and that will occurs a remaining flux will be there, and that will cause a formation of the residual magnetism. So what will happen if remnant or magnetic remnant flux or remnant magnetism present, that will effects on a residual magnetism will leads high inrush currents, and that will cause incorrect operation of the relays. Also, it will give incorrect measurements on a results, that is on a AC test results, that it will give wrong or incorrect measurements of the excitation currents, then influence of the magnetic balance test, and that will give an influence of the sweep frequency response analysis measurement. That is the DC remnant flux occurs due to the transformer shutdown or due to the winding resistance test, that will impact on a AC test results, that is excitation current measurement, magnetic balance test or turns ratio test is also there, and sweep frequency response analysis measurement. So I have taken some data. If we do not do a magnetization after the winding resistance test, here you can see there are three limbs are there, that is phases RYB. Let us consider ABC is there. As per the standard practice, or it is commonly that middle phase should have high magnetizing current with comparison of other two limbs. But here you can see yellow part indicate this is a middle limb, but excitation current is very low before the demagnetization. After the demagnetization, we will see here directly that the whatever excitation current of the middle phase is more than other two phases, that is A and B. So after the demagnetization, we will get a correct results of the excitation current. Similarly, if we see the demagnetization results of SFRA test, that is sweep frequency response analysis test, You can see red and red and blue part is there. So red indicates this is a SFRA measurement before demagnetization. This curve is not too much visible, but I will give you, that is, this is a dB to hertz, that is frequency to dB curve is there. And here you can see before and after demagnetization how SFRA graph will change. So for doing a demagnetization of the transformer, there are various methods are there. So first one is the variable voltage constant frequency, then variable voltage variable frequency, decreasing amplitude of an alternating polarity DC current, and constant alternating voltage with decreasing time. So these are four methods that are using for demagnetization of the transformer. Out of that, third one is very common and very efficient method to a demagnetization, that will give a up to 100% of demagnetization is possible with the help of method like, that is, decreasing amplitude of an alternating polarity DC current. So this is all about the demagnetization, and this demagnetization feature we have added in our instrument. So user can demagnetize the transformer after the winding resistance test, or also we have given a separate facility that whenever you want to do a demagnetization of the transformer, he can do. Okay, next part is the analysis and testing of the on-load tap changes. So we will see the basics of the OLTC and some what are the types of the OLTCs, and how to check the healthiness of the OLTC, and which feature we have added in our TRM instrument to check the behavior of the OLTC. So here you can see on-load tap changer is basically very important component of the transformer to regulating the voltage without interrupting the load current. Basically, there are two types of the OLTCs, the inductive type OLTCs and resistive type OLTCs. That is resistive type tap changers and inductive type tap changers. This is a inductive type tap changer, and this is resistive type tap changer. So basically the difference is only that for limiting a current, that the medium used, that is the inductor, and similarly for limiting the current in a resistive type OLTC, the medium used, that is the resistor. So about 30% of failures in a transformer is due to the OLTC issues. So that this is very important test, that it is important to monitor the healthiness of the OLTC. Basically, as everyone knows, the taps OLTC or tap changes on the HV side of the transformer. So now we will see basically there are two types of the resistive tap changes. The first one is the diverter switch tap changes and selector switch tap changes. So basically the difference between the diverter switch tap changes and selector switch tap changer is that in diverter switch type there are two parts, that is the selector, tap selector. Here you can see this is a tap selector, and second one is the diverter switch. In the diverter switch tap OLTC or tap selector, at here you can see the tap selector at the top and the diverter switch at the bottom, and this is mostly used in the transformer. And second one is the selector switch type, that is both selector, tap selector and diverter switch at the same point, that is common point. So this is the difference between diverter switch and selector switch. So to check the OLTC testing, there are two methods, that is static and dynamic. As I said earlier, that is static method is to check the resistance of the winding, that is associated series components, that is the conventional static winding resistance measurement, that is used to check the winding as well as internal connections, that is bushings, that is such as the connections from the bushings and the tap changer mobile contact to the windings, like that. So this method, that is static winding resistance method, that is used, that is to or assessment can be made by comparing the results with the factory results and by separate recommended standard practices. Next part is the dynamic resistance measurement. So what is dynamic resistance measurement? So basically, dynamic resistance measurement is to measure the switching process or switching operation of the diverter or selector switch. Typically, switching time we can't do with the static winding resistance measurement. The switching time of the OLTC, it is 40 millisecond to 60 millisecond. So we cannot do we cannot check the typical switching time with the help of static resistance method. So typically this method is to check the switching process of the diverter switch. So this method is used to detect the arcing contacts, switching time of the diverter switch, then switching interruptions due to the broken commutating resistors or broken leads, like that. So for dynamic resistance of the transformer, we can check with the help of graphs. So there are three methods to analysis of the various OLTCs and diverter switch. So first method is the current curve, that is current versus time curve. And second method is voltage versus time curve, and third one is the resistance versus time curve. Out of that, current versus time curve is very common method and efficient method to measure the healthiness of the OLTC through dynamic resistance measurement. So current method, with the help of current method, that we need to inject some DC current during the operation of the OLTC, that is from one position to another position, and we need to capture the samples of the current, that is percentage of reduction current during the shipment of the taps from one position to another position. It is recommended that the percentage decrement of the current should be above means below 30%. If it is below above 30%, then we will say there will be any problems occurs in a diverter switch or selector switch. So with the help of current curve, the winding during tap is sampled at high speed, and we will measure the percentage drop in current during tap change and time required to change the tap position from one tap to another tap. That time we are saying as a transition time. That is during tap changes from current to time. So here you can see with the help of our instrument, we will give a curve, that is current versus time curve. That is, here you can see current is increasing from one point to another point. After a certain stage, it will during the shipment from another to one tap to another tap. You can see decrement of current. We will see, we will check, and that data we will directly capture in a test report. That will I will show in a next slide. Here you can see, so current versus time graph facility we have provided. So with the help of our instrument, we can take all the sample data, that is resistance of every tap, then percentage decreases in a current, then transition time, that is the time required to change the tap from one position to another position. Here you can see tap number 16 is there. The resistance of that channel, it is 184 milliohm, and percentage decrease of the current, that is roughly it is 10%, and transition that required to change from 15 to 16 tap, it is 40 millisecond. Here you can see with the help of our instrument, we can measure all these data of all the phases, that is R phases, then similarly Y phases and B phases in a single click. So we will get all the results, and after that, with the help of base results or factor results, we can analyze that is there any failure or is there any problems occurs in a diverter switch or selector switch or in a winding. After that, we will analysis the same. So here I will conclude the OLTC test. That is, with the help of OLTC test through our instrument, we will plot and we will take all the data, that is transition time, percentage decrease in a current, and current versus time graph we will get with the help of our TRM instrument. So next part that we have added in our instrument, that is resistance versus time graph. That is, as everyone aware about, there is one important test that is carried out during the type test or routine test, that is hit run test, or we can say it is a temperature rise test. So during hit run test, we need to take the samples of results of resistance with respect to time. So with the help of our feature, we can measure resistance versus time graph. Also, we can get all the data with respect to the user requirement. So hit run test, as everyone aware about hit run test, the importance of the hit run test is to verify the guaranteed temperature rise for oil and winding over the ambient temperature. So it is 65 degree or 60 degree or 70 degree. So it is hit run test that we need to carry it out. And during the hit run test, we need to find out a rise in oil temperature of the rise in oil temperature and rise in a winding temperature. So this is a formula to calculate the hot winding temperature. So theta 2 is equal to resistance of hot winding divided by resistance of cold winding, 235, plus theta 1 is the temperature of the average temperature of the in a cold case, minus 235. So for the aluminum it is 225 we need to add, and for the copper it is 235. So here you can see the resistance versus time graph we will get with our instrument. This feature we have added, we can get resistance versus time through laptop only. So this is through software we can do the same. Here you can see resistance versus time graph, and all the data, that is time, then resistance of one phase and another phase. These two phases of resistance versus time we can get. Then user interface. This instrument is very easy to operate. So we have given two modes, that is standalone mode, and second one is the control through PC. If we select standalone mode, then we will get this type of display, and we have added different options are there, that is settings, tests, then records, special functions, and help. In settings we can create ID or edit ID, like that. Then test, as I said earlier, we have added different tests, that is winding resistance measurement, all tap winding resistance measurement, then demagnetization and OLTC. So we will get from test option. Records, we can save and delete the records with the help of this option, that is records. And special functions, to add date and time, this special function we have added. And help, we will get all the data of the software and the operation of the instrument with the help of help menu. If we select a control through PC, we will get this command, that is ID, IP address, and we need to connect the instrument to the PC through Ethernet cable. After selecting a control through PC, we will get this type of display in our laptop or PC, and with the help of some settings, that is create ID or edit ID, and after that we need to select tests, and after that we will get we will test all the, that is WRT, anti-WRT, demagnetization and OLTC through TC. So this is a sample test report for your reference. So user can add location, then serial number of the transformer, then ID, then make of the transformer, then rating of the transformers, then transformer type, it is there star delta, delta star, then current range user can add, then OLTC, then channel 1, 2, 3, primary or secondary, like that user can add, and after that user can get all the results of what channels that are selected. Here you can see, so all the results of channel 1, channel 2 and channel 3 we will get after the corrections of 75-degree results. Now the conclusion is that how to select a transformer winding resistance kit and what are their ideal specifications. As I recommend the following specification that user can get, that is the instrument should be capable of working in an electrostatic noisy condition in a charged EHV substation, that is up to 765. If substation is up to 765, then instrument should offer repeatability, consistency and immunity to interface the live switchyard conditions up to 765 kV levels. Then instrument should be capable or sustaining back EMF offered by larger power transformer, that is about 250 or 500 MVA type transformers having a having larger inductive loads, so that necessary protections with indications facility on an instrument itself will be available. Then instrument should have minimum 3 or 6 channels for winding resistance measurement and should have 1 temperature measurement channel. So if we need to reduce the time, I recommend users should select a 6 winding resistance measurement channel. So instrument user can do a winding resistance of 6 windings simultaneously in a one-time connection. That is one-time connection. The test leads that we need to connect to HV and LV. The instrument is capable to do a winding resistance in a single click on a single one-time connection to the HV and LV, or HV or LV we can say. Minimum selectable current ranges that should be from 10 milliampere to 25 ampere for up to 250 MVA transformers. About 250 MVA I recommend the minimum current ranges, that is up to 50 ampere DC, that is 10 milliampere to 50 ampere DC. The instrument should have measurement of resistance, best resolution should be 0.1 micro-ohm. Then kit should be able to inject variable selectable currents, so various current ranges should be there. Then kit should have facility to quick stabilization of test results. Then kit should have facility to automatic temperature correction facility for different materials of the winding, that is copper and aluminum. Then instrument should have inbuilt touchscreen display that is used for the easy operation for the user, and also facility to give a message like status of current rising in the test object, then failure of the stabilized current, warning messages during discharging of the test object, like that. The instrument should have facility of the automatically discharging the specific specimen, that is the transformer, after the testing. The instrument should automatically discharging facility will be there. Then kit, that is the instrument should have the automatic demagnetization feature that will be helpful to demagnetize the transformer after the winding resistance test or whenever user want to do the demagnetization. The kit should have able to conduct measurement of resistance of all taps with automated tap change function. This facility should be there to reduce the time to change the tap from one position to another position. Then it will also facility to check the discontinuity of the OLTC, that is to check the behavior of the OLTC from changing tab from one position to another position. Then to analyze the OLTC healthiness, there should be a facility to give a current versus time graph, that is to get the results, that is sampled winding resistance against a plot against a time in a graphical way. And instrument should have internal memory to save the results. The instrument should have the facility of Ethernet as well as USB, or Ethernet or USB facility should be there to downloading the data or to copy the data through pen drive. The instrument should be housed in a rugged model carrying case that will be useful during the transportation or shipment of the instrument. And last one is the instrument should be work on a single phase input power supply, that is through Indian socket. You can see. So last point is that interpretation of the measurement. So after the winding resistance measurement test, how we will interpret the results with base results or factor results like that. So how to interpret that? So we have original factor results will be there. So with the help of original factor results, we need to compare. Then individual phase measurement, that we need to compare the RYB phase results, and after that we can analyze. Then previous test results, if we did a winding resistance test one year back, then we can compare that results with previous test results. And one point that is given by IEC IEEE, as I said earlier, that whatever results we are comparing, that results should be at 75 degrees Celsius temperature. So for temperature correction, IEEE have given formula, that is RS is equal to RM, and this is TS plus TK divided by TM plus TK. That is RS is resistance as desired temperature, TS that is at 75 degree, and RM is the measured resistance. Then desired reference temperature, that is TS. TM is the temperature at which resistance was measured, and TK is the 235. If we transformer having a copper material, winding material is copper, then TK is 234.5, and if winding material is aluminum, in that case TK is 225 degrees Celsius. So this is all about the transformer testing. Then transformer winding resistance measurement, and Scope introduced TRM series, and what features that we have added, like transformer winding resistance measurement, then all tap transformer winding resistance measurement, demagnetization, and OLTC testing that we have seen. Now I will see some questions from chat session.
Sir, if there is any question, you can ask the same into our chat room. We can answer, because till now there is not many important questions, or whatever the questions, it has been already answered by me in the chat. However, Kiran, you can take the question of Mr. Rohit Jadhav. who has asked, is mega test of transformer is sufficient for winding resistance? Kiran, you can, I have already explained that it is a totally different test, and you can explain in 2 lines how it is different. What are the differentiation between the insulation test and the winding resistance test?
Okay. Winding resistance test is the DC current test, and the insulation test, that is the DC voltage test, we can say. To check the insulation healthiness, we need to inject, or we need to do a test with voltage, that is AC or DC. To check the resistance, we need to always inject DC current or DC voltage. If we need to do a winding resistance, we need to inject a DC current. As I said earlier, up to 20% of rated current that we need to inject, and with that we need to find out winding resistance of the transformer. And if we want to do a insulation resistance, so we need to inject a DC voltage that is recommended up to 5 kV or up to 10 kV is there. So with the help of insulation tester, that is 5 kV or 10 kV, we can measure the insulation resistance of the transformer. So this is the basic difference.
Regarding the removal of residual magnetism, Kiran, there was one more question. So if you can highlight the residual magnetism, how it can be taken out or it can be nullified if the customer is not having our winding resistance meters.
If a customer is not having winding resistance meter, then how we can nullify
residual magnetism?
Okay.
The manual process you can highlight a little bit. This will be against Mr. Syed sir's query.
Basically, sir, whenever we are doing a winding resistance test, after winding resistance test, some manufacturers of the transformer or customer of the transformer that are doing a AC testing after the winding resistance test. If we directly go AC testing after the winding resistance test, that is excitation current test or turns ratio test, or we can say SFRA test, like that. So if we go directly after the winding resistance test before demagnetization, so that will impact on a wrong results of the turns ratio or excitation current. So it is basically recommended, if we are going for AC testing immediate after the winding resistance test, it is recommended to go AC tests after the demagnetization of the transformer only. But if instrument is not available with you, so it is some manufacturers or utility customers are doing, they are waiting for 1 day or 20 hours or 24 hours. So it is normally in 24 hours transformer 24 hours, basically it is not
Kiran, I will highlight over here that generally when the automatic demagnetization is not available, sir, there are 2 ways, as Kiran was telling. One way is that, or second way is that the best way is that you complete all the AC test, like turns ratio or other test, SFRA, all those things before conducting the winding resistance, and conduct the winding resistance at the end of the all test. So DC test will be the last test on the transformer, and once the DC test is done, means winding resistance test is done, then generally we are charging back the transformer. So once we are charging back the transformer with a high voltage, rated voltage, then the residual magnetism, whatever will be remaining inside the transformer as an effect of the winding resistance measurement, that will be